Okay, moving on with derivatives. We've talked about the power rule and exponential rule briefly in class, and we're going to use those today with rates of change, which is using derivatives and tangents and secants and stuff to look at position, velocity, and acceleration. This is very applicable in physics, so if you're taking physics, you can use this stuff to answer some of your questions. If your physics teacher will allow it, they may force you to use these crazy formulas, kinesthetics or kinematics or kinesiology, I don't know, something like that. So anyway, on with calculus. Some general notes about position, velocity, and acceleration. We'll usually use S of t to denote position. Sometimes you'll see x, and position, of course, is like feet, meters, miles, etc. Velocity is distance over time, like meters per second, miles per hour, and we'll use v of t, which makes sense. Acceleration is a of t, which is like meters per second squared. I really don't know why we use S and X for position. I guess I could look that up and probably figure that out in about 30 seconds of research, but I'm too lazy. So, moving on, the relationship among those three things. S is your position function. The derivative of position is velocity, and the second derivative of position, or the derivative of velocity, is your acceleration. So you simply go down the line in derivatives. Velocity is the derivative of position. Acceleration is the derivative of velocity. So we'll just go straight down the line. We'll talk about that in more detail, or if you have any questions about why that's true, but I'm just trying to keep this video short, and I'm just going to give you the facts. So there we are. Let's see, average rate of change. We will be doing average rates and instantaneous rates of change. The average rate of change is something you've been doing for about 4 years. You just didn't know it. Average rate of change is a fancy way of saying find the slope. And if you notice this formula, if you have a function and you're doing average rate of change from a to b, it is f of b minus f of a over b minus a. That, if you notice, is simply your change in y over your change in x. It's the old-fashioned slope between 2 points. Instantaneous rate of change is where we have to tie in calculus, because now we're looking for the slope or the rate of change only at a point. And if I want the rate of change at a point, then we measure that by doing the slope of a tangent. If we're doing the rate of change over an interval, like maybe from this point to this point, well, now I'm finding the slope of a secant, the slope between 2 points. So that's the difference between average and instantaneous. And always pay attention to those words, because eventually you're going to get so used to doing instantaneous, you'll forget how to do average. Just remember, average is always your good old-fashioned slope formula. All right, so how about a real problem? An object moves according to this function, and always pay attention to units. My time is measured in seconds, and my distance, s, is measured in meters. You always want to pay attention to that. Find the average velocity from 2 to 4. So if I want average velocity, that's not calculus. That's algebra 1, algebra 2. We do it in pre-cal. Average velocity is going to be s of 4 minus s of 2 over 4 minus 2, and we simply plug those numbers in. S of 4 is going to be 16, 3 times 4 is 12, 16 minus 12 is 4, plus 5 is 9, S of 2, 4 minus 6 is negative 2, plus 5 is 3, over 4 minus 2, which is 2, 9 minus 3 is 6, over 2, and if you're into that advanced math, that will be 3. Now we just got to make sure we have our units. Velocity is measured in meters per second for this problem. So there we go. That's average velocity. It's nothing more than finding slope. You've been doing that for a long time. So that was average velocity. Before we get into some more detailed questions, some more notes here, and kind of go all over the place here, am I not? Okay, if velocity is bigger than 0, your object is moving either up or to the right. It depends on how we're measuring the distance. If we're talking about a ball bouncing on a spring, then a positive velocity would be moving up. If we're talking about somebody running horizontally, or maybe a car driving on a road, we would consider a positive velocity as moving to the right. A negative velocity is moving down or left. And one thing you need to remember is that velocity does indicate direction. Velocity does show direction, and that's how velocity and speed are different. Speed is just a raw number telling you how fast you're going. If I'm going 40 miles an hour forward or going 40 miles an hour in reverse, it's still 40 miles an hour. That's a speed. But if I were talking about velocity, going 40 miles an hour in reverse is a velocity of negative 40. So when you talk about speed, it is the magnitude of velocity. It's always measured with a positive number. While velocity can be negative, which indicates a backwards motion, be it left or down, it's a backwards motion. Speed is one of the things that's a little bit confusing when we talk about whether an object is speeding up or slowing down. A lot of people want to look only at acceleration, but if an object is speeding up, it's actually a combination of velocity and acceleration. And for an object to speed up, and that's what's happening with number 4 here, in order for something to speed up, speed is increasing. That means velocity and acceleration have the same sign. They are both positive or both negative. So it's possible to be speeding up with a negative acceleration. It just means you're speeding up going backwards, and that would mean velocity is also negative. Speed decreases when your velocity and acceleration have different signs. So in that case, you're going to be slowing down. So if velocity and acceleration have different signs, then your object in motion will be slowing down. If velocity and acceleration have the same sign, your object is speeding up. I think those are all the key notes. I had one problem, and I'm going to ask several questions with this one problem. But I give you an object in motion, I give you the position function, and I give you a note here to use feet and seconds as your units. So just kind of keeping track of that. The instant I see a problem that involves position, I will usually go right into getting the velocity and the acceleration. So while I'm looking at position here, let's go ahead and get velocity. V of t is simply the derivative. Bring down the 3, subtract 1 from the exponent. Bring down the 2 times 6 is 12. Subtract 1 from the exponent. The derivative of 9t is 9. The derivative of 1 is 0. And then my acceleration, 3t squared, the derivative is 6t. Negative 12t, the derivative is negative 12. So there's my velocity and acceleration, and now I'm going to go through and start answering the questions. We'll see average velocity over an interval. You have to be careful. This is average velocity. This is old-fashioned slope. And what's confusing is you start to get too smart for your own good. If I want average velocity, velocity is a change in position, right? Velocity is a change in position. My function s of t. So if I'm going to do average velocity, then I need to find the slope of my position function. So it's actually going to be s of 2 minus s of 0 over 2 minus 0. We actually are not going to use the velocity function for average velocity. Instantaneous velocity is different. Average velocity, though, we're just going to do the old-fashioned slope formula, so I'll plug that in. 2 cubed is 8. I should have done this off to the side. Hang on, I'm going to pause this and get my calculator ready. Okay, I'm back. Yeah, just for the sake of time, I'm going to punch these in the calculator. S of 2 is 3. S of 0 is 1. S of 0 is 1. And then 2 minus 0. Okay, punch that in the calculator. 3 minus 1 is 2. 2 minus 0 is 2. 2 divided by 2 is 1. So my average velocity over that interval would be 1, and my units are feet per second. Always include units. You will lose points if you do not put units. So there is average velocity. Let's see. Let's move on to the next question. Exact same object, same position. We've already found velocity and acceleration, which I have right here. What is the velocity at 4 seconds? All right, well, here I'm not giving you a time frame or a time span. This is at one specific point. This is an instantaneous velocity. This is an instantaneous question. So to answer that, if I want the velocity at 4 seconds, well, then I'm simply going to plug in 4 to my velocity function. And if I plug in 4 to my velocity function, you get 9. And so at time t equals 4, I'm moving at a velocity of 9 feet per second. At what time is the object at rest? Ooh, different question. We haven't done this one yet. An object is at rest. Let's see, when something is resting, it is not moving. So if something is resting, that means velocity is 0, right? Right? Am I right? Am I right? Velocity is 0 when something is at rest. So if I want to know when something's at rest, you take the velocity function, 3t squared minus 12t plus 9, and we will set that equal to 0. So I'll factor out a 3, leaves me t squared minus 4t plus 3. Keep factoring. 3, that'd be t minus 1, t minus 3. And you get t equals 1, and t is equal to 3 seconds. So when t is 1 and when t is 3, my object is at rest. It's not moving anywhere. Just for a second. What's probably happening is it's turning around. It's like moving forward, and then at 1 second it stops and starts moving backwards, or vice versa. So we're probably turning around at these points, but it is possible to go somewhere and then stop for a second and then keep going in the same direction, right? We do it all the time while we're driving. We come to a red light, we stop, and then we keep going. Now, if you're lost, then you probably stop and turn around. Anyway, so an object in motion, same function. An object is moving to the right. When is the object moving to the right? Okay, what did I say about moving to the right? An object moves to the right when velocity is positive. And then also ask when something's moving to the left, which is when velocity is negative. So to the left, that means v of t is negative. Well, we already know when my velocity is 0. We just worked out velocity. Let me go back and find it. It was, after we factored, it was 3, t minus 1, t minus 3. So we know that v of t is 3, t minus 1, t minus 3. And we know it's at rest. My velocity is 0 at 1 and 3. The way we're going to solve these problems is I'm stumbling all over myself. I like to set up a number line. And this number line represents my velocity. And on this number line, I'm first going to plot my zeros. T is 1, and t is 3. My velocity is 0. So I'm going to put zeros above 1 and 3 to represent a 0 velocity at those times. Now I need to determine when my velocity is positive and negative, and I'll do that by simply plugging in test points. Plug in something to the left of 1, something between 1 and 3, and something after 3, and we plug in those test points. I'll plug in 0, I'll plug in 2, and I'll plug in 4, and we're going to plug those into velocity. So v of 0 is, I'll plug in 0 to my velocity right here, 0, 0, that's 9. That is a positive number. That means everything to the left of 1, I'm going to have a positive velocity. When I plug in 2, v of 2, you get, actually I'm going to plug in right here because I can just look at the signs. 2 minus 1 is a positive number. So when I plug in 2, I get something positive. 2 minus 3 is something negative times 3. So 3 times a positive times a negative. V of 2, I'm for that to be 2. V of 2 is going to be something less than 0. So in that interval, my velocity is negative. And then when I plug in 4, 4 minus 1 is positive. 4 minus 3 is positive. And then times 3 will still be positive. So this interval, my velocity is positive. So now I can look at that number line and I can say, okay, my object is moving to the right on the interval. Now remember, t starts at 0, so I'm moving to the right on the interval 0 to 1, and again from 3 to infinity, and then I'm moving to the left between 1 and 3, when velocity was negative. Let's see, when is an object speeding up? Okay, well remember, speeding up means acceleration and velocity both have the same sign, so what I'm going to have to do here is look at my acceleration. I'm going to have to set my acceleration equal to 0. My acceleration is 6t minus 12. Set that equal to 0, and you get t is equal to 2. And what I'm going to do is the exact same thing I just did with velocity. I'm going to do the number line for acceleration because I need to know when my acceleration is positive and when my acceleration is negative. So if you remember, let's go back to that page. Where was it? Here it is. An object is speeding up when velocity and acceleration have the same sign. So we have to do that whole sign chart with acceleration, and we're going to compare it to velocity. So acceleration, I know, is 0 at t equals 2. And then I'll plug in a test point. I'll plug in maybe 1. If I plug in 1, 6 times 1 minus 12 is negative. If I plug in 3, 6 times 3 minus 12 is positive. Okay, yeah? And then I take my velocity number line and I compare the two. So I'm going to take my velocity number line. Here's velocity. And I'm going to bring it right down here. I'm going to try to keep them lined up to where my numbers are are in order. So I have 1, 2, then 3 kind of lined up there. And in order for something to speed up, I want to find the places where acceleration and velocity have the same sign. So let's see if we can figure those out. Let's see, acceleration and velocity have the same sign. Let's see, right here between, oh, that's too faded. There we go, right here. Between 1 and 2, acceleration and velocity are both negative. So in that interval, my object's speeding up. And then everywhere after 3, acceleration and velocity are both positive. So on that interval, my object will be speeding up. So my answer to number 5 is going to be 1 to 2, and then again everywhere after 3. Yeah? An object speeds up from 1 to 2, and then everywhere after 3. Good, good? Any questions, comments, concerns? All right. Let's see. I'm actually going to, I want to get a copy of this velocity one more time. Last question. What is the total distance traveled from 0 to 4? I'm going to spend a little bit of time on this. How much time have I spent so far? 16 minutes. So hopefully we'll finish this in 20 minutes. Total distance is kind of a thorn in our side in this class, or it has been in the past. What a lot of people want to do for total distance is they see, oh, distance is a measure of position, right? Distance is a measure of position, which it absolutely is, so we are going to need the position function. But where most people go wrong is they think total distance, let's do my final position, let's find out where I end, where I finish. So I'm going to plug that in my calculator real quick, and I get a final position of 5, and then an initial position when t is 0, I'm starting at 1. So they think, okay, well, I started at 1, I ended at 5. Well, that's a total distance of 4 units, or in this case, 4 feet, right? Wrong. It doesn't work that way. What that is, if you do ending minus beginning, that's called displacement. Displacement is different than total distance. And the best way I can describe that for you is, let's pretend that this is my house. Actually, that's kind of big for my house, but there's my house. And let's say this is the school. So here's Spain Park. And let's say that I am driving along the road and I go 10 miles to this point. And then I realize that my left tire fell off. My left rear tire fell off, and it's sitting on the side of the road right here. So I initially go 10 miles, but then I realize that my car is falling apart. So I turn around and I go back. And we'll call that 5 miles. So I go 10 miles, then I go back 5 miles, and then I go the rest of the way, which is 15 miles. So I went 10 miles forward, 5 miles backwards, and 15 miles forward again until I got to Spain Park. Well, my total distance traveled is 30 miles in this example. But that included some backtracking. My displacement is, let's see, that was a distance of 5, right? So 5, 15, my total displacement was 20 miles, but because I did some back and forth, I increased total distance, and that's what we have to figure here, because this problem actually does have some back and forth action to it. That may have been a bad example. I just kind of freelanced that one. So to get total distance, what we have to consider is the direction that we're traveling. This was our number line for velocity, and we said that from 0 to 1, my object actually traveled to the right because velocity was positive. But then I stopped at 1 and I started traveling left. I turned around. So from 1 to 3, I actually moved backwards and I backtracked. But then once I got to 3 seconds, I turned back around and started going forwards. So we've got to figure out what is the distance we traveled backwards and forwards and all this mess. And what I'm going to do is I'm going to organize this a couple of different ways. I start at t equals 0 right here. And my initial position at 0, and I'll do this over here, my position when I started was 1. So I start at a position of 1. Well, then I travel for a whole second, and then I stop. So I'm going to find my position at 1 second. And my position at 1 second was 5. So I traveled all the way to a distance of 5 for 1 second before I turned around, right? So I'm going to turn around right here at t equals 1, and that was a distance of 5. Or that was at a position of 5, a distance of 4. And I traveled to the left until I got to 3 seconds, and then I turned around then. So S of 3, I've got to find my position at 3. Y1 of 3, I get 1 again. So actually what I ended up doing is I turned around and I went all the way back to my beginning point. So at 1 second, I turned around. I started going backwards again. So now I'm going backwards. And at 3 seconds, I stop again, and I turn back around. And then I travel to the right until I get to 4 seconds, because I'm asking on the interval 0 to 4. So at 4 seconds, my position is 5 again. That's kind of interesting. So I travel to the right, and then I'm stopping right here at t equals 4. So what we initially thought was a total displacement of 4 units, because I started at 1 and I ended at 5, it actually ends up being 12 units, because I went 4 to the right, then 4 to the left, and then 4 back to the right. And my total distance, so I went 4 units, so I went 4 more units here, then I went 4 more units there. My total displacement, or my total distance traveled, is actually 12, and in this case, feet. That's a lot of traveling. So you have to consider distance traveled forward and backwards when you turn around when you're going to answer a total distance question. So there that is. I was hoping for 20 minutes. I went to 21. I'm such a loser. All right, well, I'll see you tomorrow.